So is that bright enough? Should I turn off the lights in the room? Is that okay? It's okay with that, with the lights on? Okay. Yeah, I think it's okay for the camera, isn't it? Yeah. Okay, so this is going to be our last lecture related to LIGO and other Earth-based interferometric gravitational wave detectors. On Wednesday, if all goes well, Bill Hamilton from Louisiana State University will give a lecture on gravitational wave detection using bar detectors, that is resonant mass detectors. He's coming out just to teach this class, but he'll also then as an add-on give a Jaguar seminar on Thursday about the current status of work on bar detectors. And then next week we'll move on to Lisa. So this lecture will come in two parts. I'll talk about the ultimate limits on how well one can do in gravitational wave detection using the facilities that we have for LIGO as they're currently built. Now, one can make improvements on those facilities. This is Ron Drever and I will both remark. But with the facilities as they now stand, there are certain limits, which I'll discuss. And then Ron Drever will talk about advanced techniques for third, fourth, 17th generation gravitational wave detectors that could push down to those facility limits and very likely beyond eventually. So on this transparency, I am showing the facility limits as three curves that are put on top of LIGO noise curves. So the LIGO noise curves are the initial interferometer curve, the advanced interferometer curves for a broadband detector and for a narrow-banded detector. And we're plotting frequency running from 10 hertz to 1,000 hertz. And square root of the spectral density of H running from 10 to the minus 4 per root hertz up to about 10 to the minus 21 per 10 to the minus 24 to 10 to the minus 21 per root hertz. But because we imagine in the future pushing below 10 hertz, I'm showing these facilities limits going off to the left. I'm going to talk about three different facility limits. A limit due to scattered light noise. This has to do with scattering of light in the LIGO beam tubes. A limit that's associated with Newtonian gravitational noise due to fluctuating Newtonian gravitational fields pulling on the test masses, and then a limit associated with residual gas in the LIGO beam tubes. You notice that these limits are then running from about 1.7 times 10 to the minus 25 per root hertz for this floor, and then running up as like a sort of a wall due to Newtonian gravitational noise, pushing on up to the left. The scattered light noise being unimportant, but getting it to the level that was unimportant was non-trivial, and I'll talk about the nature of that noise and how we got it down to that unimportant level. So I'm going to begin by talking about the scattered light noise as the first topic. So the nature of the scattered light noise is the following: that if you have a let's focus this a little bit. So you have the light beam in the LIGO beam tube running back and forth between a corner mirror and an end mirror. And every time the light beam bounces off, reflects off this corner mirror or the end mirror, there is a very small amount of scattering. Basically, a probability for a photon to scatter is of order 10 to the minus 6 or 10 to the minus 7. But that turns out to be enough scattering to be a serious potential problem. And so a few of these photons, remember that the amount of light that is stored in there is something like 10 to the 18 photons. So there are a lot of photons in there. And probability 10 to the minus 7 to scatter means there are something like 10 to the 11 photons actually scatter every time the light bounces off the mirror. So what happens is that a light can scatter off of this mirror, 10 to the 11 of them. It can go down, bounce off the wall of the beam tube, come back, and with a probability of, say, 10 to the minus 6 or 10 to the minus 7, scatter back into the main beam, which means that you may still get back into there, say, 10 to the 6 photons or so. So that's still a lot of photons. Well, that's not a problem until you notice that the walls of the beam tube are generally vibrating. They are vibrating due to whatever's going on in the environment. They're not seismically isolated, and so the Earth is vibrating up and down, and that triggers the walls to vibrate up and down. And so it's fundamentally, that's what the problem is. The Earth vibrates due to ambient seismic motions. The walls of the beam tube vibrate, and when they vibrate, they put on a time-varying phase shift on those photons, say 10 to the 6 of them, that have scattered and bounced off the wall, go back and scatter back into the main beam. And those phase shifts are large. Those phase shifts are of order pi. This is of order unity. And so although they're only a tiny fraction of the photons that do this, we're sensitive to very tiny fractions of a wavelength in terms of phase shift, or of a radian in terms of phase shift. And so this can become a very serious problem if we don't do something about it. And so that was understood from the very beginning of this field. And it was understood what one should do in order to deal with this. But what one needed to do was to put baffles on the beam tube to capture the scattered light. So, in fact, a set of baffles have been put on the beam tube, actually closely spaced near the end and corner stations, much more distantly spaced near the center of the beam tube, just spaced so that any light that scatters off of this mirror cannot see the beam tube itself. All it sees is baffles. And so clearly from geometric considerations, that means they're closely spaced in here. In fact, separations in here right at the end are something like 60 centimeters or so. So they're very close together at the ends. The separations get up to, I think we used about 180 meters, 200 meters separations up in here, which was closer than they needed to be. But there were other reasons for wanting to do it that way. So what happens is that when light scatters off this mirror, then it comes down, it hits a baffle, and it gets scattered off the baffle and off to some much steeper angle, and then it gets absorbed in the walls with a very small probability of making its way on down to the other mirror. The problems that remain, however, are that light can scatter off this mirror, hit a baffle, and it will not reflect. The angles of the baffles are such that the reflection would send it nearly perpendicular down to this other wall. Instead, it can scatter back off the baffle in a non-reflecting way, a specular scattering. It can scatter back off that baffle, go back to this mirror, and get scattered back into the main beam. But the probability of that is rather less than before the tubes were baffled, because these scattering angles are very shallow, and so in fact the reflectivity of the tube is necessarily relatively high for those scatterings. But this reflectivity for scattering in this specular manner, that's not reflection, this is basically reflection. That scattering probability is relatively small. And so that is, however, is one remaining issue. And the other remaining issue is that light can go down and it can diffract off of the edge of the baffles and go back up to the other mirror. So those are the two issues that remain, is the diffraction of light off the edges of the baffles and the back scatter off of the baffles. And so the name of the game then was to design a set of baffles that would control this noise. And somehow I seem to have gotten things out of order. Just give me a second to figure out what's going on here. Gosh. Well, hang on. I was rearranging the transparencies at the last minute. I will ask you to turn off the camera or edit it later. If I don't find this, then I will draw on the blackboard. No, I'm not finding it. Okay. So let me explain things on the blackboard then. Pardon? Yeah. So I want to look particularly at the issue of the scattering off of the baffles. Now suppose that let me draw the beam tube in cross section. Let's suppose this is the top of the baffles. And let's suppose that we have a mirror that is near the center of the beam tube, and the other one's near the center of the beam tube. Then light can go down, scatter off the top of the baffle, and go back to the other mirror and scatter back into the main beam. And the path length from in terms of the net phase shift that you might get in going from this mirror down to there and up to the other mirror will be about the same as going to this location and out to the other mirror, or to that location and out to the other mirror. So there's a serious danger of coherence in the scattering with things adding up coherently around the edge of the baffle. And so Aina Flanagan and I worked out a design for the baffles to destroy the coherence and also to improve or to reduce the net scattering or the net diffraction probabilities. That was to build baffles, and let me show you actually a picture of one. To build baffles, oh gee, I actually have it on this transparency. That's why I couldn't find it. I'm not very swift today. So let me show it on this transparency. So the idea is then to build baffles that have teeth on them. Teeth that stick up by distances that correspond to a phase difference in going down, diffracting, and going up to the other mirror, a phase difference between something that diffracts off this tip and something that diffracts off the valley, a phase difference of several radians. So that there will tend to be some canceling out of the effects of light that diffracts off the tip and diffracts off the valley. So you basically get some averaging out. But the idea was then to have and that's a well-known technique, in fact, in astronomical instruments as well, to reduce scattering. But in other astronomical instruments, you are not worried about coherence of scattering. And we're worried about coherence. And phase coherence. And so to deal with the phase coherence and make absolutely sure that the light that scatters off different locations is phase incoherent, we made the baffles have random heights and valleys. And it's not hard to show that the gravitational wave signal, the noise that you get, quote signal, the noise that you get from this diffracted light, goes like an integral of an exponential of I times the wave number, 2 pi over the wavelength of light, times the path length from mirror to a point on the baffle and back to the other mirror. That's the standard phase shift. But the important thing is the time-varying part of this h, and the time-varying part of this h comes from the baffles vibrating up and down, moving, say, from this height to that height. And so you have some spectral density for this particular area to be uncovered and covered. That will give rise to a spectral density of h at that same frequency. And so you look at the spectral density of the motions of the baffles for covering and uncovering areas here, and you want to integrate over the area. Now, the important point is that this integral over the area is an integral over distance here and over height. And the height is basically the time-varying thing. So it's an integral over distance of something that looks like the path length from mirror to mirror. And that path length from mirror to mirror has the relevant piece that is z, the height of the baffle. That is, the path length is shorter to that point at height z on the baffle than to this point. And so you wind up with this integral being basically a Fourier transform of the height distribution of the baffle teeth. Now, the wonderful thing about Fourier transforms is that the Fourier transform of a Gaussian is a Gaussian. And Gaussians fall off very strongly at the tail. And so what Aina and I did was to design baffles that have Gaussian probability distributions for the heights, and work with a height distribution such that the noise then was sitting way out on the tail of the Gaussian, at least to the point where you got a noise reduction in amplitude by a factor of 10 or more. And so in fact, this is a picture of these baffles. They were rather vicious to be put into the LIGO beam tube. I guess it goes, this is the bottom, it goes the other way. So here are the baffles. As you see, well, I guess that's the, well, this has to be the baffle down here. And you're looking down the dark beam tube there. This photograph was taken after installation in the beam tubes. And this is sitting physically here, this is maybe 3 times as high as the baffles actually are in the beam tube.
So that Jack was driven by a random number generator?
No, it's driven by a random number generator with a Gaussian probability distribution.
And how did he enter that Gaussian distribution? That formula, I didn't quite see it. I see it for the transform, the U to the 2 by...
Well, it's because wherever it went. I don't know what I did with it now. Here it is. So it's because you're doing an integral of e to the 2 pi I, path length from mirror to mirror is proportional to z, and you're integrating then e to the I, you're integrating this with z being some function of L. And that function of L that you have is actually Gaussianly distributed, basically, or the heights of the peaks and valleys are Gaussian distributed. And so when you when you do the integral along the edges and get a number from here, a number from there, a number from here, a number from there, it winds up being a Fourier transform of the probability distribution for the heights of the peaks and valleys. So you just have to do a little bit of mathematics. That also, let me just remark, I have enjoyed in my career from time to time functioning as an engineer. I designed rocket engines for Viacol Chemical Corporation. That was not entirely successful in the end, some people may know. I've designed baffles for LIGO. There come times when issues that are quite different from what the engineers have faced previously arise. That was the case here, the issue of coherence in the scattering and how serious an issue is and how do you deal with it. And when that issue arose, the engineers sort of threw up their hands, and Robbie Vogt, who was director of LIGO at the time, asked me and Aina Flanagan to look at it and see what we could do to scope it out and deal with it. So here is the predicted noise that we got for our specific design of the baffles, folding that into a spectrum for the vibrations of the Earth, and folding into engineers' models for how those vibrations feed up to the LIGO beam tube and the producing vibrations of the LIGO beam tube. And so the diffraction noise is sitting basically in here, and the backscatter noise there, they are more or less the same. These noises are maybe a factor of 3 higher than they have actually wound up, because the scattering, the mirrors are about a factor of 3 better, roughly, in their scattering than what we expected when we designed the beam tube. The mirrors are getting better and better and better. So this is down some from there, and gives the curves that the curve that I indicated for scattered light noise then on this other graph. This is just a rough approximation to that complicated curve coming in at a level that, as we had intended, is below other sources of noise. So that is one of the things that is a facilities limit. The next thing I want to talk about is residual gas. And to discuss residual gas, I'm going to go to the blackboard. So the issue of residual gas is that if you have your beam traveling down the beam tube back and forth roughly 100 times with a shape that is that of a Gaussian beam, a waist here at the center, so a shape something like that. So the light is all in here. There are also molecules of gas that are in this beam tube because the vacuum is not perfect, and because in particular there is gas in the metal, in the steel walls of the beam tube that comes out of the beam tube sort of randomly. So you have gas coming out randomly and gas molecules going through the beam, reflecting off the wall, going through the beam. And the fluctuating number of gas molecules in the beam causes a fluctuation in the dispersion, that is the time delay in the light travel time down the beam tube. And so one can estimate this in the following way. The index of refraction that is produced by the gas is 1 plus some constant, which is called the polarizability of a gas molecule, times the number density rho, that's the number density, not the mass density, of molecules. And so that I can write as 1 plus alpha times the number of molecules that are actually in the volume of the beam divided by the volume of the beam, the volume in which the light is concentrated. Now, this polarizability, which obviously has dimensions of length cubed, since volume is also length cubed and the index of refraction has to be dimensionless. This polarizability is particularly big for molecular hydrogen. And so a major issue in the planning of LIGO was to get metal from which the beam tubes would be fabricated that was low in concentrate of molecular hydrogen. The particular techniques that they use to make steel tend to leave a lot of molecular hydrogen in the beam tube. And so LIGO worked together with the steel industry to develop improved steel with lower hydrogen content than normal steel. And that's what the beam tubes are made out of. So, but hydrogen remains the most worrisome issue. And so let me go on and let's assume that these are hydrogen molecules. Then an important issue is the amount of time that it takes for a hydrogen molecule to move through the light beam. And let's call that tau star is the time in the beam. Or the mean time in the beam. The molecules have a random distribution of velocities. But if you just put in a temperature of room temperature and the size of the beam, you get out that this mean time is about 17 microseconds. Coincidentally, 17 microseconds is also about the time that it takes for light to travel from one end of this 4-kilometer beam tube to the other end. And so with each trip down and then return, on the return trip, one sees a different set of molecules, roughly speaking, from what you had on the previous trip. And so you can do a crude analysis of this fairly easily, knowing that coincidence of numbers. This is the the actual effective index of refraction, well, the actual index of refraction averaged over the beam tube, if n is the actual number of molecules that are encountered. But n is fluctuating, and it's fluctuating on the time of each trip down the beam tube. And the fluctuations are presumably just square root of n fluctuations. Now, they could be larger due to something going on in the beam tube causing an outgassing of a sudden burst of molecules. And we don't know a lot about that, but that's one of the kinds of spurious noise sources that would give an excess noise that one has to be prepared for. As we will see, the noise with square root of n fluctuations is relatively small, and so while this is somewhat worrisome, it's not a huge worry. So you can ask then, what is the RMS fluctuation then in the index of refraction from one trip down the tube to the next trip down the tube? And that's going to be just this expression with n replaced by the root mean square fluctuations of n, which is just for a Poisson distribution, which is what we would hope for, that square root of n. So this is 1 plus alpha square root of the number of molecules in the beam, of the mean number of molecules in the beam, divided by the volume of the beam. Now, this index of refraction is going to give rise to a phase shift on each trip down the beam, a phase shift that is just equal to n times k times L, where k is the wave number and L is the distance down the beam. So this is the noise. This is the noise, and the RMS noise in the phase shift is just n delta n RMS KL, where that's the delta n RMS. The gravity wave signal that you accumulate in each trip down the beam is a phase shift that is just h times KL, roughly within a factor of 2. And so that means that the RMS noise that is produced by these fluctuations of index of refraction is just in order, within a factor of order unity, the RMS fluctuations of n. And so that RMS noise then looks like this 1 goes away in the fluctuations. So it looks like the polarizability times the square root of the mean number of molecules divided by the volume of the beam. Okay. Now, if you think about it, what we're dealing with is shot noise, in the sense that you have shots of molecules going through the beam, each of them producing a little bit of phase shift. And so it's like the random arrival of photons. In fact, it's the same probability distribution, presumably, Poissonian distribution. And so we're guaranteed that the spectral density of this noise is going to be white. That's the case for all shot noise when the duration of the shots is small compared to the periods over which you're computing a spectral density. And our periods are milliseconds, and the duration of the shots is something like one trip down the tube, something like 10 or 15 microseconds. And so that means that this HRMS is going to be equal to the square root of the spectral density times, well, let me start over again. HRMS we can get by integrating the spectral density of H with respect to frequency from 0 to the maximum frequency involved in the shots and taking the square root. That's how you always compute the variance, is by doing that integral, and take the square root to get the RMS fluctuations. What is this maximum frequency? That's 1 over tau star, the duration of time that the molecule spends in the beam. And so that tells us that HRMS is approximately then the square root of S sub h times 1 over tau star, But that tells us that S sub h is approximately this HRMS, which is alpha square root of n bar over the volume of the beam times the square root of tau star. So the actual formula is somewhat more complicated than this, but this captures the basic ideas and gives a good order of magnitude estimate. What we see is that the spectral density, I'm sorry, this is the square root of the spectral density. Okay. So the amplitude noise, square root of spectral density, scales the square root of the mean number of molecules in the beam, which means square root of the pressure in the beam tube. The pressure that LIGO is designed to operate at is a pressure of about 10 to the minus 9 torr of hydrogen. The torr is one of those units that is almost as obscene as astronomers' units. It's a millimeter of mercury. But it's about 10 to the minus 3 of an atmosphere. And so this is about 10 to the minus 12 atmospheres. So it's a very good vacuum. But the beam tubes are so good, so free of leaks, that this vacuum is maintained by ion pumps that sit at the ends of the beam tube. And I think, is there one ion tube at the center of the beam tube? Ion pump at the center? Yeah, so there's one down here, there's one at 2 kilometers down, and one down there. And that's enough to maintain this vacuum, though the original pumping down to get near that level was done with cryo pumps.
Can I ask you a quick question?
Yeah.
In reality, the optical path variations of the beam experience is really along the whole arm line.
That's right.
So really it would be an integral of the index of refraction along that path.
That's right.
And so you will have a distribution, a spatial distribution as well as time distribution
That's right.
of the number of particles.
That's right.
When you do all that integration...
When you do all that, and the light has a Gaussian profile, so this is not a precisely defined volume. And you have to be concerned about the fact that as you make successive trips down the tube, the gravity wave signal builds up with a number of bounces linearly, but the noise builds up as the square root. So there are factors like that that come in that mean that this is only good to within an order of magnitude or 2. This gives you the general idea. But doing the correct analysis is a lot more than this. But this gives you the idea of what's going on in the physics.
And the transfer function, so when you made the analogy with the short noise, is doesn't quite enter as a short noise at time t. It's really distributed over...
It's really distributed, but those all the relevant times for the molecular motions and so forth are short compared to a gravity wave period. And so it still is shot noise. You're still in a long wavelength or low frequency limit compared to the durations of any of the shots. So the bottom line of this, if I can now find my transparency that I want. Just give me a moment. Bottom line of this is the residual gas noise that I showed you that sits at about 1.7 times 10 to the minus 25 per root hertz. I don't see where that, oh, it's over here, okay. So let me just put it on top of the predicted noise from so we have the diffraction, well, we have the light scattering noise, we have the residual gas noise, and the residual gas noise dominates over the light scattering noise above about 10 hertz when you take account of the improved reflectivities of the mirrors for light scattering. So I have one more noise source to talk about, and that's seismic noise. It turns out that the dominant source of cause of seismic noise is fluctuations in the density of the Earth that are produced by ambient seismic waves going through the Earth underneath and in the vicinity of the LIGO test masses. And so here is a picture of that. So you have a LIGO test mass sitting on the Earth. The Earth is vibrating up and down, and there are high-density regions, low-density regions, high-density regions as a seismic wave goes by. And so the high-density regions pull on the test mass, and low-density regions, at least relative to the average gravitational force, they push on the test mass. The test mass is pushed back and forth as the wave goes by. This noise source turns out to be quite significant at frequencies below about 10, maybe in advanced interferometers, maybe even 20 hertz. Let me say just a little bit more about it to give you a feeling for what's involved.
So you're not worried about seismic wave? How big the seismically isolated?
It's seismically isolated, and this is something that the seismic isolation is a major issue. But this is something that is in addition that you must also deal with. So this is a separate issue you must also deal with. The wavelengths that we're concerned about, well, the frequencies we're concerned about are around 10 hertz. The speed of the seismic waves ranges from about 250 meters per second in the rather loose material at the top of the, near the surface of the Earth, of the LIGO sites, to 6,000 meters per second when you get down to the bedrock, which is down a few kilometers. And the waves that are predominantly responsible for this gravitational noise have are confined near the surface, and so they turn out to have speeds that range from around 300 to 600, maybe approaching 1,000 meters per second, depending on how deep they penetrate into the Earth. The further down you go, the better the Earth is compacted. Both sites you're dealing with alluvial material, basically, and not with bedrock until you get down quite deep. But this alluvial material, sand or clay, when you have a lot of pressure on it, the particles of sand or clay are pushed against each other more strongly, and as a result, they're more capable of propagating sound. And so you get quite a variation in sound speed as you go down, just by tens of meters. The wavelength at 1,000 meters per second is about 100 meters. At 300 meters per second, the wavelength will be correspondingly only about 30 meters. And so we're talking about wavelengths of that kind of a scale for these seismic waves. The damping lengths, well, the thing you need to know is that the Qs, the quality factors for propagation through basically any kind of geophysical material, whether it's bedrock or sand, they range roughly from 15 to 30. Oh, they may get down to 8 and they may get up to 60, but 15 to 30 is a characteristic number. So material doesn't, normal geophysical material absorbs these waves rather easily. That means that the damping length, the e-folding length at speeds of 1,000 meters per second is about 1,000 meters. And our speeds may typically be half that, so maybe 500 meters. And so there may be 8 e-folding lengths from one end of the beam tube to the other, which means that this stuff we're worried about is locally produced in the vicinity of the ends of the beam tube by people, by rain, by loggers, felling trees, by trucks, and so forth. And so I say, sources are local: wind, rain, cars, planes, people, oil pipelines. There's an oil pipeline that is a little problematic near the facility in Louisiana. Scott Hughes and I carried out a detailed modeling of these waves as part of Scott's thesis, detailed modeling of these waves at the 2 sites, at the Livingston site and the Hanford site. And from that modeling, we were able to deduce or determine a range in which the Newtonian gravitational forces would lie. And for lack of time, because I want to say one more thing, let me just show you the result of the calculation. I'll give you a paper which you can read or browse that gives you details. It really depends on how noisy the ambient noise is. And it's much more noisy in the daytime. It's much more noisy at rush hour, even though there aren't that many cars in the vicinity of the sites. Still, at 5 in the afternoon, it's a lot noisier than it is at 2 p.m. And so this is sort of a range, sort of a mean range through which the noise may vary. You notice it's not all that far from the advanced interferometer sensitivities. And it is really a potential problem when we get to things that go beyond LIGO 2, beyond the advanced interferometers. So I want to just at the end say something about one other form of gravitational noise that is a potential problem and that we have designed the facilities to deal with, and that's noise produced by human beings. This is also something, I mean, I enjoy doing things like this, and so I also did this particular one. And this is work that I did with my wife. My wife is a professor at USC, and her field of specialty is human motion. And so she told me what I needed to worry about, or we figured out going back and forth between us what we needed to worry about. Turns out the dominant source of noise from human beings is walking. Nobody walks smoothly. There are jerks. At the moment you put your heel down, there's a jerk. And when you push off with your toe, there's a jerk. And so what the people in her field, which is called biokinesiology, do is for other purposes than this, but their data are just there, and we just used data that she had. People, they have a force plate, and they measure the horizontal force exerted by the feet as a person walks. And the issue is that if d is the distance between a test mass and a human being who's walking, the gravitational force of that human being is gm over d squared. And I'm not talking about a quadrupole component now, just the ordinary 1 over r component. The issue is that as I walk and I push off, I push against the floor, and the floor then responds over a distance that is big compared to my distance from the test mass. So basically its response in terms of moving sort of averages out. And much more important is the effect of my gravitational pull. And so what we're concerned about then is just the time variations in the distance of my center of mass to the test mass. Well, the thing they measure is the horizontal force, which is m times the second time derivative of d. And what that horizontal force looks like is this. When I'm swinging my leg to move forward to take the next step, I go from a force that is positive, depending on whether I'm back here, to a force that's in the opposite direction as I swing my leg. And so the force as a function of time goes like that. When my heel goes down, there's a sharp change. And as I'm shifting my weight from one foot to the next, this force goes booming back up, and then a gradual decrease. So there are near discontinuities, that is changes on times of 0.03 seconds. That's 1 over 30 hertz at heel down and at toe off. And those rather sharp changes give rise then to gravitational force spectrum that is predominantly in the range from 30 hertz on down to lower frequencies. And so Carolee and I went through the details of this and wound up with a bottom line for this noise that said, as a bottom line, that we have to keep human beings at distances d bigger than 10 meters from the test masses, or we would have problems. So the facilities were designed so that nobody is within 10 meters of the test masses when LIGO is in operation. Well, I'm going to turn this over to Ron to talk about how one might get down near the facilities limits. But let me just introduce what Ron has to say by looking at LIGO noise sources and in the advanced interferometers and comparing them to the facilities limits. So here are the facilities limits, the gas noise, which could be lowered by putting additional pumps on the beam tubes, and there are provisions, there are places where those pumps could be put on if you ever needed to lower it. But there's where it sits. Here's the gravity gradient noise, which is possible to deal with by cutting back on human activity and various other techniques, by putting dampers or improved dampers on the vibrations of the beam tube. Oh, I'm sorry, no, not that. Got it. Let me start over again. This is the gravitational forces. So there you have to cut back on the Earth motions, but since the Earth motions to a great extent are due to humans, that you have to control human activity. But that's what we've got to deal with, we think. And this is the quietest of the Earth motions, when things are very quiet. The noises in LIGO 2 are thermoelastic noise, that is the worst kind of thermal noise coming in along here with the current design, with reshaping the light beams the way that I would like to do. We may pull it down actually in LIGO 2 to about there. There is the optical noise that Buonanno and Chen talked about in their lecture. And there is seismic noise. That's the vibrations of the Earth, as opposed to the gravitational forces from the vibrations of the Earth. And there's suspension thermal noise. Suspension thermal noise and thermoelastic noise you can deal with by cooling, and Ron will talk about that. Seismic noise you would have to deal with by a more effective seismic isolation system. And the optical noise you have to deal with new designs for the optical topology of the interferometers, like Yan Bai Chen talked about, quantum non-demolition interferometers. And all of these things are under discussion in the LIGO scientific community. Sometime in the next year, there will be a major session at the LIGO scientific collaboration meetings to try to map out a tentative strategy for how one might go with LIGO 3 in terms of dealing with these noise sources to push down toward the facility's limits. So Ron, let you talk about some